Hello, my name is Julian Osorio, and today I'll be doing the video for the Lab 4 Fluent Project simulation. So first, let's start with the geometry of the wind tunnel. Let me open it. So starting from the Lab 1 where we created our wind tunnel, keeping the same geometry, I just edited the sketch and inserted this flat plate in the middle. The height was 2.7 millimeters and the length was 22.9 centimeters. So converting that, just putting it into the wind tunnel. And then once you finish the sketch, you go to concept, surface from sketches, and then you generate, and then it should create the wind tunnel with the flat plate inserted here with this space. Once we're done there, we close, and then we open the mesh. Once we're in the mesh window, we keeping the same mesh from when we first made the wind tunnel. You could see here with the triangle method and the 3000 uh, 0.003 element size. We have to insert the name sections like you did with the velocity inlet, pressure outlet, and velocity walls, but this time with the the flat plate top, flat plate bottom, front, and back. Once we have those, we can come up to generate the mesh, generate the name sections to create the full mesh for the flat plate with inside the triangle method. Next, we go to setup, and this is where we start the Lab 4 report on all the things we need to find. The first thing we'll need to find is the velocity contours and with the velocity vectors. Next would be the laminar boundary layer velocity profiles at the three locations. And then we'll have to plot the wall shear stress along the flat plate along with the local skin friction coefficient. And then finally get the drag force coefficients for the flat plate. And we'll do that once this loads. Looks good. So first we come here to materials, air, close. I'll close this. We'll go to boundary layer conditions, velocity inlet. Wait, this is the velocity inlet that we would get when we did the 20 hertz for the simulation. This is what we get for the velocity in to match the velocity of the test section. So apply and close. We'll close this. Well, we go to reference values, make sure it's the same for the velocity, and then we go to initialization and then initialize. Wait for that to load. Once that's done, we come down here to run calculations. We set it to 100 iterations just to get a decent amount of data, and then calculate. Okay, now it's done calculating, we can start with the report. To get the velocity contour and vectors, we go down here to graphics, we'll go down to contours, and then we'll make a contour. So first we start with the velocity magnitude, we had to select the fluid that's on the surface body, the velocity inlet, the pressure outlet, and then the front plate walls with the wind tunnel walls. We click Save and Display. This is the velocity magnitude across the wind tunnel. As you can see, the velocity at the inlet is lower, but as we get closer to the test section, the velocity increases, and then you can see the effect that the flat plate has on the velocity at the surface layer, and it gets further from the surface of the flat plate, and then we could see the effect of the wake region behind the flat plate and how it affects the rest of the velocity as it goes through the wind tunnel. We'll close this, and then we'll close this, and then we'll go to vectors. We'll go to vector 2, and so vector velocity with the same surface body, the velocity inlet, pressure outlet, and the flat plate walls and wind tunnel walls selected, and we'll click display. And then we could see here the velocity vectors at every point along the wind tunnel, how it changes throughout the wind tunnel. At this edge of the front plate, you could see how the velocity is affected by the plate at the tip of it, and as you go along the flat plate, as you can see, the arrows get a little lighter, indicating that the velocity is getting lower, the velocity magnitude is lowering as you go along the flat plate. And then once you get to the edge of the flat plate, you could see how the end affects the velocity as well. And then the effect of the flat plate along the rest of the wind tunnel through the diffuser. Now that's the part A for the velocity contours and velocity vectors. Next, we're going to plot the laminar boundary layer velocity profile. So we'll close here, we'll close vectors, we'll close graphics. We'll come here to plots, XY plots, plot 5. Here we have x1, y0. We'll go here to velocity. Well, first we have to position it on the y-axis. Then we'll change this to 0, 1. And then we come here, we click down here, velocity. And then we'll have at the 3 points that we measured with the real blue wind tunnel at the 0.2 centimeters from the front of the plate, 8 centimeters from the front of the plate, and 16 centimeters from the front of the plate. So if we click the 2 centimeters, the way we have it with our wind tunnel, you could see the where the edge of the wind tunnel is where we measured, and then we'll get this plot. As you can see, as you go higher in the y direction away from the top of the surface of the flat plate, the velocity profile increases until you get to where the free stream velocity is back. Next, if we move on to the 8 centimeters from the front of the flat plate, save plot, it looks a little nicer, but it's still the same. As you get further away from the flat plate, the velocity increases until you get back to the free stream velocity at the velocity of the wind tunnel. And then lastly, at 16 centimeters from the edge of the flat plate, it'll look similar. It's just as you get further from the top surface of the flat plate, the velocity will increase, getting closer to the velocity at the test section until it hits the boundary layer where it's 0.99 of the velocity test section. That's part B. So next we plot the wall shear stress along the flat plate. So we'll go back here. We set it back to the x-axis. We'll change this back to 1, 0. I'll move here, move this down here. So once we have that, we can set this y-axis to the wall fluxes, and then here we have wall shear stress. We'll come up to here, and then we'll go down, and then have the top surface of the flat plate selected, and then we'll click Save and Plot. So as you can see, at the beginning of the flat plate, it's an initial high wall shear stress, and as you go down the flat plate, the wall shear stress decreases until you reach the end of it. Next, That's part D. Next, to plot for part E, to plot the local skin friction coefficient, we go down here, set the y-axis to skin friction coefficient, and then save plot. You can see here it's about 2 minus to the e minus 1. And here you can see that skin friction coefficient is a little lower, but it's kind of the same graph. Initially has a high skin friction coefficient. As you go down the plate, it'll gradually go down until you reach the end of the plate. And then for part F, we'll close all of these and then we'll come up here to report definitions. We'll go set to new, force report, drag, and then we can click here drag coefficient, which is what we want to find. If we click you can, since we made the name sections at the mesh with the top, front, bottom, and back, we can individually see the effect of this drag coefficient, but for now we just want the top. Compute, this is what we get for the top drag coefficient, but if we click all of them, you can see uh, compute. This is the drag coefficient for all 4 sides. There we go. And that is all for the video that we were required to show. Thank you for watching, and that's it.